In 1869, a Russian chemist named Dmitri Mendeleev sat down to write a chemistry textbook. He needed a way to organize the 63 elements that were known at the time because he wanted to present them in a logical order that made sense to students. And what he created out of this was instead one of the most extraordinary intellectual achievements in the history of science. He arranged the elements by their properties, and then he discovered that those properties repeated in a similar and predictable pattern. He organized that pattern into rows and columns on a table. And then he did something that amazes me every time I think about it. He left gaps. So not because he ran out of elements, but because the pattern told him that elements must exist in those gaps. Those elements actually had not yet been discovered, but he predicted their properties in detail. So every single one of those predicted elements was later found, and they were exactly where he said they would be. With the exact properties that he described. So the periodic table is not just a chart on a classroom wall, it's a map of actually matter itself. And once you understand how to read that chart, the world looks different. My name is Dr. Colleen Spiegel, and this is the Tesla Institute. So the story of the periodic table begins not first with Mendeleev, but with the discovery of the elements themselves, and with the scientists that were trying to make sense of a growing collection of substances that seemed to follow these hidden rules. In the early 1800s, the chemists had identified dozens of elements and noticed something that really puzzled them. Certain elements seemed to behave similarly. So elements such as lithium, sodium, potassium, these were all soft metals that react violently with water. Chlorine, bromine, iodine, these are all reactive nonmetals that have similar chemical behavior. And he hypothesized that these similarities probably couldn't be accidental. There had to be an underlying order. So in 1864, an English chemist named John Newlands discovered that when elements were arranged by atomic weight, every eighth element had similar properties. And he called this pattern the law of octaves, which is named after musical octaves. So his colleagues ridiculed him at the time, but his theory broke down with heavier elements. So his presentation was imperfect and it didn't yet gain traction. But then came Mendeleev. In 1869, Mendeleev arranged the 63 known elements by their atomic weight and noticed the same periodicity. But he was a lot more rigorous and more bold. Where an element did not fit the pattern he expected, he did not force it into the table. Instead, he concluded that the atomic weight must have been measured incorrectly, and in several of those cases, he was right. And then where the pattern demanded an element that had not been found, he left a gap there and described what the missing element should actually be like. He predicted the missing element in detail along with the properties and called them ecoboron, ecoaluminum, and ecosilicon. Within 15 years, all three of these elements were discovered. You have scandium, gallium, and germanium, and these matched Mendeleev's predictions with remarkable precision. What fascinates me about this story is what it says about the nature of science at its best. Mendeleev did not just organize what was known. He trusted the pattern enough to predict what was not yet known. That combination of empirical rigor and bold inference is what makes the periodic table one of the greatest intellectual achievements in human history. And here's what actually makes it more remarkable. Mendeleev did not know exactly why these patterns existed. That explanation would not come until the 20th century with the development of quantum mechanics. He saw the pattern decades before anyone understood what caused it. So let me explain how the periodic table is actually organized, because once you understand the structure, the properties of every element become predictable rather than arbitrary. So the modern periodic table organizes elements by atomic number, which is the number of protons in the nucleus, rather than the atomic weight as what Mendeleev used. The atomic number is more fundamental and eliminates a few inconsistencies in Mendeleev's original arrangement in his table. So the rows on the periodic table are called periods, and elements in the same period have the same number of electron shells. So the layers of electrons that orbit the nucleus in Bohr's model. Hydrogen and helium are in period 1, 1 electron shell. Lithium through neon are in period 2, 2 electron shells, and so on. So the columns in the table are called groups. The elements in the same group have the same number of electrons in their outermost shell, which is called valence electrons. This is one of the key insights with these. The valence electrons actually determines how an element behaves chemically and electrically. So this is directly connected to what we covered in the electricity video. Copper, which is the metal in every electrical wire, is in group 11 and it has one loosely bound valence electron. And this moves freely from atom to atom. That single free electron is why copper is such an excellent conductor. On the far left portion of the table, the groups 1 and 2, these contain the most reactive metals. 1 or 2 valence electrons that are easily given up. And on the other side of the periodic table, in group 17, these are the halogens. They're 1 electron short of a full outer shell. So these are extremely reactive because they're trying to grab that missing electron to fill their valence shell. All of these elements, their goal is to have a full valence shell. And nothing in nature can be unstable. Everything goes to energetically to a level of stability. So group 18, the rightmost column is called the noble gases, and these do have full outer shells. So these are completely stable. So they're almost entirely unreactive. So these elements, helium, neon, argon, the elements, these don't want nothing from anything, basically. There's also a diagonal trend from the upper right to the lower left of the table, which separates metals from nonmetals. And there's a fascinating band of metalloids in between here. These are elements like silicon and germanium. They have properties of both. What fascinates me every time I look at this table is that all of this, every chemical reaction, every material property, every electrical behavior, flows from one number, the number of protons in the nucleus, and then everything else, all the other properties in the table follows from there. Now let me connect the periodic table to energy because the elements that make modern energy technology possible are scattered across the table in ways that tell a fascinating story. So element 29 is copper. Nikola Tesla understood copper deeply. His alternating current system, the electrical system that powers the world today, depends on copper's extraordinary conductivity. Copper has 1 free valence electron per atom and has the lowest electrical resistance of any common metal. So every transformer, every generator, every motor that Tesla designed was wound with copper wire. The global electrical grid, Tesla's greatest legacy, is essentially a copper network spanning the planet. So element 78 is platinum, and we discussed platinum in the fuel cell videos. This sits in the transition metals region of the table, which is the large block in the middle of the table, and its position explains its catalytic properties. Transition metals have partially filled d-electron shells, which allows them to form temporary bonds with reactant molecules. And that's exactly the property that makes platinum such a great catalyst for splitting hydrogen and oxygen for fuel cells. The challenge with the platinum is its rarity and its cost, which is why reducing platinum loading in fuel cells is one of the most active areas of electrochemical research. Element 3 on the periodic table is lithium, and this is the lightest metal on the periodic table. It sits in the top left corner of group 1. And its low atomic mass and single valence electron makes it ideal for battery applications. Lithium-ion batteries dominate portable electronics and electric vehicles because lithium can store and release electrical energy efficiently while keeping batteries lightweight. Element 14 is silicon. Silicon sits on the metalloid diagonal between metals and nonmetals. It has semiconductor properties, so intermediate electrical conductivity, which can be precisely controlled, which actually makes it the foundation of modern electronics. So all our circuit boards, our computers, everything that we're basically using all day on a daily basis, and also solar cells. The photovoltaic effect converts sunlight to electricity in solar panels, and this depends on the silicon's unique position in the periodic table. Element 1 is hydrogen. This is the simplest element. It has 1 proton and 1 electron, and it's the most abundant element in the universe. It's the fuel of the stars, literally, and increasingly the fuel of a clean energy future. Hydrogen sits alone at the top of the table, It's sometimes placed above the alkali metals because of its single valence electron. And it's sometimes actually placed above the halogens because it could also gain an electron. So it has unique properties. It belongs in both groups and kind of a neither group, which is a fitting position for an element as versatile and important as hydrogen. There's also the rare earth elements. So the bottom two rows in the periodic table, the lanthanides and actinides they're rare earth elements. Even though the name says they're rare, they're not particularly rare, but their unique electron configurations give them magnetic and optical properties that are found nowhere else in the periodic table. So neodymium and dysprosium are essential for powerful permanent magnets in wind turbine generators and electric vehicle motors. Lithium is used in nickel metal hydride batteries. Europium and terbium create the colors in LED lighting. So that clean energy transition in our economy depends critically actually on rare earth elements, which creates a technological opportunity, but also a geopolitical challenge, since most rare earth production is concentrated in a small number of countries around the globe. So one of the things that continues to fascinate me about the periodic table is that it's not finished yet. Element 118, oganesson, was confirmed in 2016. It actually sits in the noble gas column, which is the group 18, and it should, in theory, be stable and unreactive because it's in that group, like the noble gases above it. But quantum mechanical calculations suggest that these electrons are behaving differently than expected, making it potentially more reactive than a noble gas should actually be. So the periodic table predicted the properties of undiscovered elements for over 150 years now. But at the heavy end of the table, the predictions start to become a little less certain because there's fast-moving electrons near heavy nuclei change that sometimes changes their behavior in ways that we're still trying to understand. So scientists are currently working to synthesize elements 119 and 120, which would actually begin a new period in the table. So the properties that they'll have and what group they'll fall into and whether Mendeleev's patterns will still hold true at these extreme atomic numbers are open questions at the frontier of chemistry today. The periodic table is still one of the most successful organizing principles in all of science, and it's still not complete. So Nikola Tesla worked with copper his entire career. The conductors, the coils, the motors, the transformers, all built from an element whose properties flowed directly from its position in the periodic table. Every energy technology we've discussed so far on this channel and then upcoming, which is fuel cells, batteries, solar panels, wind turbines, these all depend on elements whose properties are explained by the periodic table. Platinum catalysts, lithium anodes, silicon photovoltaics, rare earth magnets, hydrogen fuel. The periodic table is not just chemistry. It's a map of what makes modern energy and the modern world possible today. So Mendeleev left gaps because he trusted the patterns. The elements were found exactly where he predicted. And this is what good science looks like. Finding the pattern that's deep enough to see what has not yet been discovered. So subscribe to the Tesla Institute for more chemistry, physics, electricity, and engineering. The sciences that together explain how energy in our modern world works and how we can harness it. My name is Dr. Colleen Spiegel, and I'll see you in the next video.